So each dx contributes its own dep. We just have to think about how to put it all together. Let's actually sort of plot it first and think about it. If we were to say, here's the x-axis again, from 0 to L, that means your rod is basically sitting here, and your little dx was somewhere in the middle. So let's think about its contribution to the electric field, its dep. And actually, we don't want to just plot dep, because how much it contributes depends on how big you make dx. We aren't really saying how big, thick, how wide dx is. It's an arbitrary thing. We're just saying it's some small width. So actually, how wide dx is tells you how much charge it has. Okay? So its width actually counts. So let's say we're going to look at dep per little width dx. We're going to plot dep per dx over x, the different positions of these dx's. That's what we'd really want to think about. So here, at this position, somewhere in the middle, you get some value, right? I mean, we could start the plot that way. As you get closer to point P, right? So point P is out here somewhere. As you get closer to point P, it's going to go up. It's going to be higher. As you get farther from point P, it's going to go down. Okay? When we get x equals 0, it's not going to 0. It's just going to some value. The dx over here is still a charge. It still creates a field. This dx is closer, creates a higher field. So if you were to plot it, it would look something like this. It would kind of go up like that. And actually, if you look at it mathematically and you plot it, what you're plotting is dq over what? A plus L minus x squared. You're really just plotting some function that looks like that. So now, you could ask yourself, what do we do now? We have all these DEPs. Well, what does each one really contribute? If you plot it like this, what it's really contributing is if this is its dx, if it's a piece that wide, it's really contributing this area. It's contributing this much to the field, right? If you wanted to know what's the area of that little rectangle, it's that value, dep over dx, times this chunk dx, then that's the area. So you could actually get the dep of this one if we plot it this way. If this dx is way up here, since dep per dx is higher, it's going to have a larger area. This one, dep per dx is smaller. It's going to have a smaller area. So what we want to do is figure out how to add it all up. Okay? Well, you can probably guess, maybe you've seen these kinds of plots before. We need to add up the area under this curve. So what you do is you sum them up. Right? You integrate. So I'm giving you a little bit of an intuition for how you would sum these up as an integral. Since this isn't a calculus class, we're not going to do it in detail. Okay? But you may recall from calculus that doing this, dealing with integrals and derivatives, depends on a formula where you assume the limit where dx goes to 0. And this is where we answer Mr. Cruz's question. Okay? When you're dealing with electrons, that charge goes to a certain small value, but it's a finite point charge. Here, this dx can actually go to where its width is 0 and its charge goes to 0. So this is truly the differential element of a continuum. It doesn't shrink down to a point charge. It shrinks down to nothing. And having the limit where that goes to nothing is what lets you do integrals and derivatives. So that's as far as I'll go sort of explaining it. So let's sum them up like this. Now, when you integrate, you're going to add these up to get what we're really looking for, the E field at P. This is really what we want. Okay? What we have is a bunch of DEPs, so we need to sum them up. So you know you write a symbol like that. Okay? To help you remember that's a sum, make sure you know that's actually an S. The integration symbol is an S. It's how they used to write an S. If you go look at like the US Constitution, every time there's two S's, one of them is this giant. Right? So I don't think the founding fathers invented calculus, but there is a connection there. So integral signs are sums. We also have to integrate the other side. Okay? So the other side was the integral of k. It was dq, and on the bottom it was a distance a plus L minus x squared. And of course, these are both in the I hat direction. I don't need an I hat there because that's a vector. Okay? So that's our integral that we have to deal with. So adding all these up just gives you EP. Really, this is what we want to integrate. So when you're faced with an integral like this, the first thing you got to think about is, what axis are you integrating along? How are you doing it? Here, we're adding up along x, right? So that means anything that changes, everything needs to be put in terms of x. Everything that you can needs to be switched to x. And everything that's just a constant can come out of the integral, okay? So let's see, k is a constant. We can take k out of the integral. This is ke, by the way. We're integrating, and dq. We need to get dq in terms of x. Well, dq, how do you figure it out? What is the charge on this little piece? It's the charge density lambda times the width dx, right? So dx really is a length. So we can write lambda dx up here. And the bottom part, a is a constant, it just stays there. L is a constant, it just stays there. Minus x is already in terms of x. I hat. All right. All right, so we're getting there. What else can we do? We can pull the lambda out. So I can just do that manually here, save a little time. Paid for it. So we have the integral of dx over a plus L minus x quantity squared. And again, this isn't calculus class, so I'm just going to do these integrals. It helps me to kind of think of this as a plus L minus x to the minus 2 and put it in the numerator. But you can integrate however you want. The integral of this would be, let's see, the minus 2 would become minus 1, so that would bring a minus 1 out there. And then it would be over a plus L minus x to the minus 1. But then you also have to divide by the derivative of this thing with respect to x, which is minus 1. So you end up with a positive like that. Okay? So the integral is lambda ke over a plus L minus x. Well, it's in the bottom. I don't have to write minus 1. There it is. What else do we need? We need limits. This integral needs limits. When you're just doing integrals in calculus, you can ignore the limits. It's an indefinite integral. When you're doing real physics problems, you have to have limits. So the one thing that we didn't do is think about what is our domain here. So we're integrating from 0 to L. So really, it's only EP if you go from 0 to L. 0 to L. That means we have to evaluate this integral from 0 to L. Okay? So what do we get? We get lambda ke over, if we plug in L, we get a plus L minus L. That's 0. So we get lambda ke over a. And then minus, and then we plug in 0, lambda ke over a plus L. And that whole thing times I hat. In the end, that's the answer. That's pretty much it. We could simplify it a little bit. We could pull out lambda ke. But pretty much that's the final answer. So that is the E at point P. When you do problems like this, you sometimes want to think about the fact that actually we've not only solved it for a distance a, we've actually solved it for any distance a. If you were asked to find the E field along the axis of a charged rod at some separation as a function of x, say, you actually could do it this way and then just plug in x here. If you wanted to calculate how does this change with separation, you could say, well, a is a separation, and you could plot it that way. But here it was just a question of what's the value at exactly point P.